Hi folks, thanks for joining me again for another webinar on decentralized identity. Today we're going to look at some of the decentralized identity protocols and standards. My name's Richard Astley, I'm one of the solutions architects with Condatis, and I'm joined here today by Mikko Varainen, a senior developer with Condatis. So this is the second webinar in the series covering decentralized identity in SSI. If you missed the first one, you can catch up with getting started with self-sovereign identity on the Condatis YouTube channel. In the last webinar, we gave a very gentle introduction into the world of self-sovereign identity with a look at wallets and the concept of a digital wallet. We looked at our identity and how we can move away from using centralized identity providers to a much better decentralized way of managing and sharing our identities. We also looked at the trust model that allows this all to happen safely and securely. In this webinar, we're going to dive a bit deeper into the standards used in decentralized identity. We'll look at the verifiable credential and verifiable presentation standard, learning what zero knowledge proofs are, and then take a look at DIDs and their DID documents in more detail. We'll also look at a couple of the protocols currently being used along with these standards, focusing on Aries, Hyperledger and SIOP and the agents and wallets which use these protocols. We'll discuss interoperability challenges and finish with a demo of a real decentralized identity system, followed by a Q&A session. I'd like to hand you over to Mikko now to take us through the standards.
Thanks, Richard. Sorry, it took a while to find the correct mute button, but yep, good afternoon, everyone. As said, we'll first take a look at the standards that are used in decentralized identity. So let's start with the standard that's in the very core of it. That's the verifiable credentials data model. So the verifiable credentials data model is a recommendation by World Wide Web Consortium. It specifies a standard way to express credentials on the web. It's designed to be secure, respects privacy, and can be verified by a machine. And verifying here means that a software can see if the credential is really from the issuer it claims to be from, and if it has been tampered with. In a previous webinars, we learned about digital wallets and the digital credentials they hold. So the information in a verifiable credential is similar to physical credentials like passports or driver's license, but the digital counterpart is more trustworthy and tamper evident because of technologies like digital signatures. Digital credentials are also more convenient to use, especially over a distance, and they improve privacy in many use cases. The data model in the specification includes the core concepts of claims, credentials, and presentations. And these are then specified using concepts like identifiers, types, proofs, and so on. Here's an overview of how a verifiable credential can be used. So first, an issuer issues a credential, and the holder accepts the credential in their wallet. And this could be, for example, a driver's license that is issued to a person after they pass a driving test. So the holder can then use the credential to create presentations and share them with the verifiers. Later on in the webinar, Richard will explain issuing and verifying with the demonstration. But first, we'll take a bit of a closer look at the specification and how it defines claims, credentials, and presentations. First of all, a credential contains a number of claims. A claim is a statement about a specific subject, it can be expressed as a subject-property-value relationship. So let's take an example of a claim. Here's Mikko works at Condatis. In this claim, Mikko is the subject of the claim. Works at is the name of the property, and the value is Condatis. So that's fairly straightforward. We can express any number of these kind of claims about the subject and put them into a verifiable credential. The claims in the credential can also be about multiple different subjects if needed. Another element of a verifiable credential is metadata. This is information like the issuer of the credential, evidence checked by the issuer before issuing the credential, date when the credential expires, or information on how to refresh the credential if needed. So essentially, when the claims are information about the subjects, the metadata is information about the credential itself. And these are just examples of metadata that a verifiable credential might contain. The data model specifies many other concepts for potential credential metadata, and also an extension mechanism to specify custom metadata to help using the credential in specific context. So all this metadata is part of the verifiable credential. The final element of a verifiable credential is the cryptographic proof. It can be used to verify that the credential is issued by the specific issuer and that it has not been tampered with. So the proof is the key element that makes the credential verifiable. A typical proof mechanism is a signature that is calculated from the credential claims and metadata. But the specification doesn't standardize any specific proof mechanism. So the proof can be anything that can verify the authorship and authenticity of the credential. The proof details can be embedded with the credential, or the credential can use an external proofing mechanism that wraps the credential. So that's the structure of a verifiable credential as it's defined by the data model specification. Here's an example of how a verifiable credential might look like as serialized JSON. So you can see there's the claim works at inside the credential subject property. There's the embedded proof in the end, and the rest of the metadata properties like context, issuer, and type. So this is what a credential might look like when it's stored in the holder's wallet. When a verifiable credential is used to, for example, prove nationality or date of birth, there's a layer on top of the credential itself to protect the privacy of the subject. This layer is called verifiable presentation. A verifiable credential is not transmitted to the verifier as it is, but instead, the verifier gets a presentation of it. The presentation includes one or more verifiable credentials, but the credential in the presentation is not the same credential that the holder have in their wallet. Instead, a new credential is derived based on the data that's in the original credential. This derived credential only includes the information that's required by the verifier. A verifiable presentation can contain one or more of these derived credentials. And this is how the verifier can access the underlying claims about the subject. Similarly to verifiable credentials, a verifiable presentation also contains metadata. Common presentation metadata are identifiers, types, and holder information. The verifiable presentation must also have a proofing mechanism. Just like with the verifiable credentials, the proof can be embedded or it can be external. And just like with the credentials, the verifier can use this proof to verify that the presentation is from the holder and it's not being tampered with. Again, here's an example of what a verifiable presentation looks like as a serialized JSON. The verifiable credential property here contains one verifiable credential with the claim that the subject works at Condatis. So you can see the metadata here also at the top and the embedded proof at the end. Privacy is an important part of the verifiable credential specification. One of the key cryptographic mechanisms to implement the privacy aspect is zero-knowledge proofs. So let's take a closer look at how it works. As I mentioned, a verifiable presentation can hold credentials that are derived from another verifiable credential. This is possible using zero-knowledge proofs. It also allows sharing a value that is derived from a claim without sharing the credential that contains the claim, but still maintaining the ability for the verifier to verify the authorship and authenticity of that claim. A common example of zero-knowledge proof is a proof of age, for example, proving that the age of the subject is over 18 based on date of birth, but without revealing the exact date or age. But the mechanism is useful for other things as well. It allows combining multiple credentials from multiple issuers into a single presentation and selecting which claims from a credential to reveal. It also prevents the verifier from identifying the original credential that they might use for correlating details of the subject. Let's take a look at the example of using zero-knowledge proofs. In the example, the verifier requires two pieces of information. Is the subject over 18? And where did they work at? The holder, in this case, has two separate credentials that can be used to provide the information. So is over 18 can be derived from the date of birth. And the workplace can be taken from the second credential. When using zero-knowledge proofs in this way, the proof in the derived credential is not the signature of the original credential, but a proof that the holder knows the original signature. So this way, the verifier doesn't get hold of information that could be used to identify the original credential, which is crucial for the privacy of the subject. But they can still trust that the original claim was authentic. So this is how verifiable credentials data model standard specifies verifiable credentials and presentations. Let's take a look at the other core standard for decentralized identity. That's the DID, or Decentralized Identifiers. Decentralized identifiers is another specification by World Wide Web Consortium. It describes a way to assign a decentralized verifiable identity to a subject. A subject can be a person, it can be an organization, or any kind of thing or abstract entity. So the DID identifies the subject. The DID can be resolved into a DID document using a DID resolver. So a DID document describes the subject, so it contains data associated with the DID. So for example, it can contain service endpoints or public keys to verify signatures. We'll look into the details of the DID document later. Each DID has a controller, which is an entity that can modify the DID document, and so it has control over the DID. The controller is the one that decides what subject the DID identifies. The controller can be a person, or it can be an organization, or even an autonomous software. One DID can have multiple controllers, and the subject of the DID can be one of the controllers, or the one controller. A DID can be recorded on a verifiable data registry. So this is where the blockchain, or more generally, distributed ledger technology usually comes in. So the verifiable data registry isn't necessarily a distributed ledger. It can also be a decentralized file system or a database or peer-to-peer network, basically any form of trusted data storage. The DIT method specifies how a new DIT can be created and recorded on a specific verifiable data registry. It also instructs the DIT resolver on how the DIT can be resolved into a DIT document. Each DIT method has a specification that describes how it works. Let's see what a DIT actually looks like. A DIT is a specific kind of URI that consists of the DIT scheme name, the DIT method name, and an identifier that is unique for that specific method. In practice, a DIT can look like this. So here we have the DIT scheme name, which is always just DIT colon. And then we have the DIT method name, which identifies which method we should use with this DIT. So this is usually the part of the DIT that tells us which technology stack the DIT is used in. In this case, the method name here is sov, which means that the DIT is associated with sovereign DIT method and their distributed ledger. We'll look into the interoperability between different methods later. Finally, there's the ID, which is a unique identifier within this method sov. When we see this kind of URI, we can tell that it's a DIT because it has the DIT colon syntax, and we can also tell that it's using DIT method called sov, and based on that, we can, for example, use a resolver to resolve the DIT into a DIT document. A DIT URL, on the other hand, is something that we can use when referring to a specific resource. A DIT resolver can take a DIT URL and use it as an input and return a resource as an output. This process is called DIT URL dereferencing. The resource might be, for example, part of the DIT document or a set of public keys related to the DIT. The structure of the DIT URL is similar to any commonplace URL. So at first, it has the DIT, which is exactly what we have here above. And it has all the optional parts of path, query, and fragment. And here's an example of what a DIT URL might look like. A DIT document is a collection of properties that describes the subject and verifies the controller. So let's go through an example of a DIT document. The DIT subject is identified in the ID property. A DIT document must always have a specific subject, and it must follow the DIT syntax that we saw on the previous slide. The controller specifies the entity or entities that control the DIT document. There are also several properties related to verification. So these are, for example, verification methods and the related public keys that can be used to authenticate the DIT subject or to verify a signature. We can also use the DIT document to discover service endpoints related to the DIT subject. So these can be any kind of services that allow further interaction, for example, messaging services or identity management services, or even just public websites. So that's an example of a DIT document. A quick summary at this point of the standards that we went through. So we went through the verifiable credentials and DIT standard, and they give us a way to identify a subject using a DIT. And we also have a way to express claims about the subject using verifiable credentials. And we can do it in a way that the individual has total control over their identity. These are the standards that define the common factors in decentralized identity. They are key parts in developing interoperable identity solutions that are really decentralized. But when we are building the solutions, the standards alone don't give us all the necessary pieces to complete end-to-end solutions. So in this next section, we'll take a look at the two set of protocols that fill in the missing parts. Each of them has a slightly different approach to the problem. First one of the two is called Hyperledger Aries. Hyperledger Aries is an open source project that provides tools for building decentralized identity applications. It includes a number of RFCs. It's a quite high number. I think it's like 97 at the moment. And those RFCs specify and describe protocols for communication between the different parts in the decentralized identity infrastructure. One of the main concepts explained and specified in Hyperledger Aries is DIDCOM. The communication is based on establishing a connection between two agents, for example, issuer and holder. And once they have an established connection, they can send messages by following a specific messaging protocols defined in Aries. An example of an Aries protocol is issue credential protocol, which describes how an issuer can issue a verified credential to a holder. Another one is a present proof protocol, which describes how a verifier can ask for a holder to share a verified presentation with the verifier. Here's a picture to explain a bit about the context where the Hyperledger Aries sits in. Hyperledger has many other projects as well. For example, Hyperledger Indy is the implementation of the blockchain side of things with the resolvers and blockchain nodes. And Hyperledger Ursa is a cryptographic library, and it's used by both Indy and Aries, and it can be also used directly by an application that's built on top of the stack. So Hyperledger Aries includes many tools and libraries that make it much easier to build applications for decentralized identity. And we'll later have a webinar that's dedicated to Hyperledger Aries, so this is just a quick introduction. But essentially, Aries is a relatively well-established set of protocols and tools for implementing solutions based on verifiable credentials and decentralized identifiers. And it's also filling in some of the missing pieces in the specifications. I will now hand over to Richard to introduce the second protocol stack and dive a bit deeper into the interoperability.
Thanks, Miko, for talking us through the standards in more detail and taking us through Hyperledger Aries and where this fits in with decentralized identity. I'd like to show you another approach to decentralized identity now, which is SIOP with OpenID Connect. So SIOP, or self-issued OpenID provider, is part of the OpenID Connect core specification. It's the part of the specification that allows for personal self-hosted OpenID providers to issue self-signed ID tokens. In the world of decentralized identity, a wallet is a SIOP, and it uses OpenID Connect to communicate, to send and receive messages between agents. Self-issued doesn't mean it self-attests all the information it's going to include in its message, just that it will sign the message and that they can be verified. So the wallet of SIOP agent signs the tokens it issues when communicating or sharing verifiable presentations. And just like Aries, SIOP defines how credentials are issued and how verifiers can ask for proof of a verifiable credential. OpenID is already a widely adopted standard in the development community. It's used as an identity authentication mechanism, and it's been thoroughly tested over time. People are already familiar with the flows and tokens expected when messaging. SIOP's just the same as any other OIDC flow. There's just a few new parameters and claims involved, like the new request parameter where a JWT token can be added when issuing credentials or when requesting proofs. This JWT describes what's needed to satisfy the request. Verifiable presentations are also returned using JWT tokens that contain verifiable credential claims, which is the normal process when using OIDC. By using OIDC SIOP, this should allow for easy adoption of self-sovereign identity using this technology, as it's already trusted and familiar within the community. The last part of SIOP I'd like to talk to you a little bit about is the distributed ledger technology that's used with SIOP, and that's the ION network. Microsoft uses SideTree and the Identity Overlay Network, or ION, to provide a way to locate a decentralized identifier, or DID. It's used to find the public keys to validate a holder controls the DID, and to provide a destination to find out additional information about that DID, like we saw with the methods and service endpoints available in the DID. The Identity Overlay Network's a public, permissionless, decentralized DID overlay network that runs on top of Bitcoin, and it leverages the SideTree protocol. SideTree is a blockchain agnostic protocol that was designed to support a globally scalable, immutable append-only log with no central provider or authorities, so this is censorship and tamper resistant. This is accomplished by leveraging decentralized ledger technology to support and distribute public key infrastructure. This DPKI is used to anchor public keys to validate ownership of the DIDs. So ION is a DID method that uses Bitcoin and SideTree, and the use of Bitcoin network as the ledger enables for massive scale, cost efficiency, and deployment flexibility. Now that we've looked at the standards and some of the protocols, it's time to think about what they're all used for, and that's agents and wallets. We spoke about wallets and the user being able to choose between them. Currently, there's many different wallet providers. We have Evernym's ConnectMe wallet. We have a Trinsic wallet, which is another of the Aries families of wallets. And then we have SIOP wallets like Microsoft Authenticator. We'll also have web wallets, and there's many more wallets out there and many more currently in development, but they can all be categorized or grouped by the protocol standards and encryption that they support. Along with many different wallets, we also have many different agents to interact with them. We have enterprise agents, which we use to issue and verify credentials. We also have cloud agents, which we use to provide a variety of roles. These can be enterprise or consumer agents. We have consumer agents that are really the wallets that we store our credentials in. And there's also mediator agents, which forward messages between agents. So let's think about it all. The wallets use agents, the issuers use agents, and the verifiers use agents. Each of these agents communicate using one of the protocols discussed previously. So they all communicate with either DIDCOM or OIDC and DID-SIOP. This kind of leads us on to the next topic, which is interoperability. So now that we've looked at the open standards and some of the protocols used to provide decentralized identity, let's now look at how they are being used and implemented. There are many different members of the identity community that are all working together to create, agree, and push the technology forward. They all share the core belief that people should hold and control their own identity. They should be able to choose what parts of their identity they want to share and when they share it, choosing where or who they share it with. They should also know and have control over why they're sharing it and control how they're going to share it. The standards answer the what, when, where and why, but it's the how that causes the interoperability challenge when issuing and verifying their credentials. What wallet will the user be managing their identity with? What agent do I need to use to communicate with the user? If a person can choose how they hold and manage their identity, just like the physical world, they can choose which wallet they want to do it with. And although wallets and agents all implement the same verifiable credential standards, they can support different proof mechanisms with different cryptography, and they use different messaging protocols and ledger technologies. It's these differences that make interoperability a challenge, as we don't currently have a super agent that talks all protocol. There's lots of work going on between the members of the community to make these groups of agents all interoperable. The Aries group of agents are becoming interoperable with each other, and the SIOP agents are becoming interoperable, which is a great start. There's also some great progress towards standardizing the way agents can exchange data when issuing and requesting proofs, which is in the presentation exchange standard. This standard is supported by SIOP and should be implemented in Aries wallets in the future, and I'll give a single standard that defines how to make and issue and proof requests to a wallet. In order to further support interoperability, Condatis are working on developing a handshake protocol, which will allow a wallet to specify what protocol it supports when handling the initial issuance of proof request when calling back to an agent. The wallet starts the process by scanning a QR code or using a deep link which contains a URL and a request URI parameter. When the wallet makes the request to the URL, it'll add a header into the request to identify what protocols it supports with a MIME type. And using this MIME type, the server that's handling the request can delegate it to the correct type of agent to issue a credential or request proof using the protocol expected by the wallet and specified using the handshake MIME type. Condatis are implementers, and we know our customers will want all that's available in the decentralized identity space. So we've been working on being able to deliver systems that will work with all the different kinds of wallets and agents. We've done this by creating a middleware. Our middleware is an abstraction layer that removes all the complexity of supporting the many different wallets and agents away from the client applications. This allows the client applications to focus on their normal business processes and only providing the data that needs to be issued in a credential. Some systems don't even issue credentials and just need to verify a credential to complete actions like account registration or to grant system access, or really to provide any other service which is dependent on the user's identity. We've developed a Condatis Staff Passport portal which can issue and verify credentials, and a Condatis Credential Verifier mobile app. We've also developed the Condatis OIDC bridge, which allows you to request and consume verifiable credentials using standard OIDC flows, which can easily integrate with any pre-existing system which uses OIDC. Now that we've talked about the standards and protocols, I'd like to show you a demonstration now of the Condatis Staff Passport system. So I've prepared a small demonstration here, and I've got a website which is a Condatis Staff Passport system on the left hand side, and I've also connected a mobile phone up for this demonstration. And on the mobile phone, you see I've got Evernym's Connect Me wallet. This is a brand new install, and what I'd like to show you today is I'd like to show you a Staff Passport system issuing out a credential to this wallet. And then I'll use the Staff Passport system to verify that credential. I've also configured an OIDC bridge to map an email scope across to the email address credential that's been issued as part of the Staff Passport. and I'll show you a relying party that's going to make a request for the email address and show how this can be shared back to a relying party using OIDC. So on the left hand side of the screen, I've got a sign-in page for the Condatis Staff Passport portal. I'll just click the sign-in option here, and this login's provided by Microsoft Azure Active Directory with B2C. Now, I'm already signed into this application, so what I'd like to do is I'd like to manage of contacts. Now, this system's dependent on a set of contacts that we create, and then we can issue a credential out to this contact. So I'll just fill in my own details just now here. So it's first name, last name, mobile number, email address, and an employee ID. So I'll just make up an employee ID for myself just now, and I'll generate this. And what this is doing is this is created the local record, which is going to be used as a key for the credentials that I issue out. As part of creating the contact, it's going to make a connection with my wallet. So if I confirm that I'm happy with this, it gives me two options on how I want to create that connection with the wallet. So for demo, I'm going to use a QR code. So if I click the QR code option, the Staff Passport portal is going to talk with a middleware, and the middleware is going to invoke the Evernym agent that can communicate with this wallet. So you should see I've got a QR code now displayed on screen that's going to start the initial connection request. And if I go to my mobile phone, I can select to scan the QR code. So if I scan the QR code now, it asks me whether I want to accept this connection or not. So if I click on the connect option, it's going to create that connection, and what this now means is the agent that the Condatis Staff Passport middleware is using and the agent on the mobile phone now have exchanged keys and can securely communicate with each other. Now that I've created the contact and I have a credential, I have a connection with the user's wallet, what I'm going to do is actually upload or issue a credential now. So I just have to upload a profile picture to complete the contact. So once I've uploaded this, I can actually start the issuing process. So if I click to issue myself a credential, I'm going to issue my first name, my last name, my email address, and my mobile phone number. Now I'll click to preview this and have a look at the credential that's going to be issued. And if I'm happy that this is the correct information, I'm going to actually issue the credential. Now what this is doing now is it's using the agent, the enterprise agent, and it's going to push a credential out to the mobile phone, to the wallet. So you should see the new message pop up on the wallet. Now this is saying that it wants to push a new verifiable credential out to the wallet, and it's whether I want to reject or accept this into my wallet. So I can see the details here. It's got a date of issue, my email address, first name, last name, and mobile number, and also my photo and a serial number. So I'm happy to accept that into my wallet. Now at any point in time, the user can go in and have a look to see what details are contained within the credentials that have been issued. But what I'm going to do now is I'm actually going to go and verify a credential using the Staff Passport portal as well. So if I'm happy that I've done this, I'll come back out to my main page and we've got an option to verify a credential. So I'll click on the verify option, and again, this is going to look to have the agent make a connection with the Connect Me wallet. The QR code again to do this, and again go to my wallet and I'll scan this QR code, and you'll see an option here, connection already exists. This is because I'm using the same agent that I issued the credential with. If this was being verified through a separate agent, then I would create another secure connection with that agent, and then it would make a proof request to the wallet. But you can see here, because the connection already exists, it's just pushed through a proof request. So if I have a look at this now in the wallet, we can see what it's requesting proof of. So again, it's asking for proof of my whole staff passport, really. So it's asking for all the attributes from that credential. So if I'm happy that I want to share this out to the Condatis Site Pass portal, I'll click send. So what's happening is the wallet will sign that and create the proof and send this on to the verifying agent. The verifying agent does all the security checks to make sure it's not been tampered with. It validates the issuer against the DID document. And if all of these checks pass, it'll show that it is a proper verified credential. And you can see the details that have actually been shared from my wallet. So again, first name, last name, email address, and mobile phone number. So this shows you our client applications using a middleware to issue and verify credentials. The last part of the demonstration I'd like to show you is what we call our OIDC bridge. And what this does is allows relying party applications that use the OpenID Connect standard for authentication or authorization to make calls for scopes that are mapped to verifiable credentials. So what I've got here is I've got our OIDC bridge management portal, which I've already registered a relying party to. And what I'd like to show you is just a couple of options that are available within our bridge. So I've registered this new relying party and I've configured a scope to make this available. So if I have a little look at the scope that I've created, I've registered an email scope. And if we have a look at the details here, the email scope is being mapped to my email address attribute from the credential. So what this scope does is it says that a relying party, if they ask for an email scope, this will be mapped to the email address attribute from a credential. There's also an option here to filter the value of those attributes if we wanted to restrict it to a specific email or a certain length of value or any other value that can be restricted using a regular expression here. We also have options to restrict this at the wallet level, so we can ask that the email attribute has to be from a specific verifiable credential schema, or that it's come from a specific issuer, or that it's from this credential definition. So you can restrict what values or attributes we're going to allow to be mapped to the email scope. I'm not going to specify any of this just now. I'm happy that this can be satisfied with any email address, regardless of what issue or credential it's coming from. We've also got a couple of personalization options available on our bridge, and this is really a little bit about the logos of corporate branding that can be used within the bridge. We can also do corporate branding using custom CSS styles, so the look and feel of the bridge can match your relying parties, and then custom links that we can use to provide links to privacy policies or terms of use. So this is a couple of the options that can be configured on our bridge, and what I'd like to actually show you now is our sample relying party using this configuration to request the email address from the verifiable credential that we previously issued. So what I've got here is I've actually got a sample relying party that I've created, and we've set it up here that we can put in a configuration. This would normally be hidden from the user interface and be an application setting in the background, but for demonstration purposes we've exposed it so we can try out lots of different relying parties all from the same sample application. So what I'll do is I'll just copy in my client ID and my client secret. And we're interested in the email scope that we'd configure that was going to be mapped to the email address attribute. So if I'm happy that all these details are correct, I'm going to click submit here. And this is going to request from our OIDC bridge to communicate with our middleware. And it's currently all configured to use Evernym's Connect Me wallet, but our middleware can be configured to talk with many different agent types. This could quite as easily be Microsoft's option, and it would be an agent that communicates with SIOP and did SIOP. But for now, this is configured using Evernym's Connect Me wallet and their corresponding agents. So what I'll do now is I'll go back to my wallet again, and I'm going to scan the QR code to make the proof request from our bridge. So if I do that now, and again, it's all using the same agent, so the connection already exists. But what you should see is the proof request coming into this mobile phone in a moment. Okay, so we've got a new prompt showing up again, the same as the Staff Passport portal. But this time it's only asking for the email address to be shared. So if I'm happy that all I want to do is release my email address, I'll click the send option here. And again, the wallet creates the verifiable presentation, creates the proof request using its proof mechanism, sends this to the Condatis middleware to the agent to be verified. Once it's verified, it will forward this on to the OIDC bridge and be converted into a JWT token with the email claim that can be consumed by the OIDC relying party. So you'll see here the relying party's got the claims that have been issued as part of the token, and you can see here that we have an email address attribute that's been shared to the relying party. So I've shown you a demo of Staff Passport clients for issuing and verifying credentials, and I've also showed you our OIDC bridge, which we've created to allow you to easily integrate decentralized identity into your existing OIDC services. I hope the demonstration was useful to show you a decentralized identity system in action. It kind of brings it all to life when you see a working example. So let's sum up today's webinar. So today we showed you a deeper look at the standards of verifiable credential and verifiable presentation and some of the different properties which make up the models. We showed a DID and its corresponding DID document to see how the verification methods and service endpoints are described. We looked at the two main protocols in decentralized identity, Aries Hyperledger and SIOP, and highlighted the key difference, which is really the messaging protocols and the ledgers that they use. We looked at a couple of different wallets and the different types of agents used in decentralized identity and the interoperability challenges with using them. I then showed you an example of a decentralized staff passport system to bring it all together. I'd really now like to just finish up with any questions if we have any. Miko, have we had any questions come through?
Yes, so thanks, Richard. A really interesting demo, and we've got some couple of interesting questions here. First of all, about wallets and mobile phones. So the question is, if I get a new mobile phone or switch from iPhone to Android, will my new wallet contain all my credentials from my old wallet? Or is everything stored in the device and lost if I don't have the old wallet anymore?
Yeah, unfortunately, right now that is the case. Your wallet's all secured with keys that are specific to that device. So what you would really have to do would be export the credentials from one wallet and restore them onto another phone. So right now, they're not backed up online. Everything's secured on your device for a good reason. It's more secure if they're stored locally, and generally the wallets are protected with biometrics, which normally means that the security that's used to encrypt the data at rest's protected by possibly a hardware key or the TEE, the secure enclave of the phone. And unfortunately, any new phone would need different keys to the chips that have first encrypted it. So there is lots of work going on to make it easier to back up and restore your credentials. But it's not as simple as just downloading the app again and having all your information. But you can download it and then just have the credentials reissued to you.
Right, yeah, that makes sense. Also related to the applications as wallets, there's a question, where's the border between a wallet and an agent?
Okay, yeah, that's a good question. So yeah, if we think about agents are really what talk in the protocols. So it's agents that communicate with other agents, whether that be as part of the process of issuing or requesting proof of a credential. A wallet has a larger job to do than the agent, really. The wallet's about providing a good user experience and UI for a user to manage their identity with. It's also about the cryptography that is used for protecting that data. And a wallet actually has an agent for when it needs to communicate with other agents. So the agent's really the protocol and the communication side of it, and the wallet's an application that uses an agent. I hope that answers the question.
Yeah, I think so, yes. So still, I think these wallets and mobile phones is the most kind of a tangible part of this. So another question on that, what if I try to issue a credential and the recipient's phone is offline?
Okay, yeah, that's a good point, to be honest. So you'll see the flow there. We created a connection with the wallet. So that means there's two agents there that have this secure communication channel that they can use anytime they like. Now, obviously, a mobile phone's not on all the time. So if that mobile phone's off, there's actually a cloud agent that handles the initial issuance request or proof request, and that cloud agent will hold that request until the mobile phone comes online again. Once that mobile phone comes online, it broadcasts to this cloud agent, and the cloud agent can push down the proof request or issuance, whichever it be. So there is this dependency on a cloud service that'll forward messages on to you. It can also be a mediator that can forward messages between different agents.
Okay, right, yes. Maybe one more question before closing up. It's on the a bit more to the about the standard. So where's the line between the standards and the kind of stack specific implementation? So I'll maybe can try and answer this one. It's more related to the standard section. So
thanks, Mikko.
Yeah. So I think the key thing there is the communication between the agents. So there's the standard for representing the verifiable credentials, and then the standards for the decentralized identifiers. But they only describe the content, and Rich has already touched on that at some point. So they mostly just talk about the content, but they don't really define how the communication between different parts work. So at the moment, at least, that's where most of the implementation-specific protocols come into play. The work on those protocols is ongoing, and also the, for example, the DIT standard is a draft at the moment, so there might be updates on that as well. So there's ongoing work to make those protocols more widespread, so they could be shared between different implementations. But I think at the moment the line is that the standards define the content and the core of the content, especially, while the protocols define the communication. I think that's all the questions we have. So, any words you want to close up, Richard?
Thanks, Miko. Yeah, so yeah, thanks for listening to today's webinar. And please join me again next month for the third in our SSI webinars. We'll take an in-depth look at Aries Hyperledger. And if you missed any of our previous webinars, they should all be available on our Condatis YouTube channel. We'll also have our B2C webinar series, which will continue in 2 weeks' time. So if interested, please come along and listen to Dave Downs talk about federation and single sign-on for Azure AD B2C. And please get in touch if you've got any suggestions on other areas of topics you'd like us to cover in a webinar series. And I'd just really like to say thanks again for joining. Yeah, I'd also like to thank Miko. So thanks, Miko, for taking us through the standards today. And for anyone out there, if you're interested in our decentralized identity solution, contact us on info@condatis.com and we'll get you set up with one of the specialists. But again, thanks very much for your time today, folks. I hope you've enjoyed the webinar, and I'll talk to you all next time.